I see. There was a second stop set. So anyway, yes, Cory is someone that I have known for a while. Back when I was regularly visiting Harvard for their clean air research center, subsequently redubbed the Air, Climate, and what was E? Environment?
Energy
Center.
Yeah.
And Cory was leading a project on, I don't remember exactly, was it causal inference?
Yeah, it's causal inference in power plants, basically.
That's right. Anyway, I learned a huge amount from him. He published with Francesca a really landmark paper that has been made a big splash quite a few years ago on using causal inference methods to evaluate the policy implications of the Clean Air Act, the regulatory effects on mortality and the extent to which it was mediated through actual changes in air pollution as opposed to having direct effects other than that. So I think we're going to be hearing a bit more about stuff like this today, as well as some new work that I was able to share through one of my visits there on interference, and you will hear more about that from him. Yeah. So with that, I think, and I should finally say that he's no longer at Harvard. He moved, took up a faculty position at the University of Texas, Austin. When was that, about a year ago?
About 2.5 years ago.
That long ago?
Yeah, tell me.
Okay, anyway, enough introduction. Go ahead, Cory.
Well, thanks very much. That's such a kind introduction, and thanks everyone for coming to hear what I have to say for a little bit. So when Duncan asked me to do this, he indicated that this could be informal. So I'm going to try and take you up on that offer and try and make this informal. I have slides here. And for those of you who remember a talk I gave with the air pollution group a couple of years ago, I'm not really expecting that you do, but if you do, some of this will be repetitive. But I am perfectly happy to have these slides be more or less a starting point for discussion and see what people have to say, and we can talk about it. Also, if folks don't mind, I certainly won't insist. If you don't mind, I would appreciate if people don't mind putting their cameras on. So some of you have probably given talks into the Zoom void before, and just kind of seeing that there are people on the other end helps me a lot. So I would appreciate that. Again, I wouldn't insist. If people are not comfortable with that, that's fine too.
Let me also announce, before I forget, that Cory has generously offered to hang around after the talk for a small group discussions with anybody that's interested.
If you're interested, yeah, I'd be happy to. And then also, I have two monitors. So now for those of you, thank you, have your cameras on, you're over here for me. So sorry that I'm going to keep peeking over that way. My slides are in front of me. But anyway, with that, what I'm going to talk about is some work that I've been doing more or less as Duncan described on causal inference for air quality policies. And I have this sort of subtitle here, Point Sources, Physical Processes, and Interference on Bipartite Networks. So hopefully what I mean by those things will be clear, come clear within the next 30 minutes or so. So I put a little preamble here, and this is the first time I've tried to articulate the points I'm trying to make in front of an audience. So hopefully they resonate or they make some sense, but again, I'd be happy if this is just a starting point for discussion. So in my experience, working again, mostly in air pollution epidemiology problems, although not exclusively, I have, at least in my mind, formed a little bit of a line between two distinct types of problems in quote unquote causal inference. And my focus, again, as I said, is air quality, but I think also relevant to other sort of large scale public health interventions as well, where at a very high level, I think if we can describe the quote unquote causal inference challenge with observational data or in epidemiology, the key analytical challenge being to quote unquote adjust, whatever that means, for who gets exposed to what and when. We know that these things are not random generally in most epi problems. And so we need to find a way to adjust for that, where I'm being intentionally vague with adjust, because this is obviously a huge literature. So if we view that as kind of an overarching challenge of causal inference with observational data, there's a distinction that I see, and I like to try to articulate, between what's on sort of the left column of this slide and what's on the right column of this slide. So I'll start with the left column, with what I'll refer to as a sort of a typical epidemiology question, where we're interested in the effect of some exposure, say on a health outcome. And so the example that is most commonly used in air pollution is a question like, what's the causal health effect of air pollution exposure? Again, being sort of intentionally generic. And in this type of question that I'll call the typical epi question, it is at least conceptually, practically this is very difficult, but conceptually straightforward to characterize how a person, say, is exposed. So you can think of saying, if I want to know the effect of exposure to air pollution, you can think of a personal monitor sitting on someone's shoulder, measuring what they're breathing at all times, as being something like a gold standard for measuring what they're exposed to. Now, I understand that that's a very technologically difficult task, and we don't really know how to do this. But conceptually, it's straightforward what it means to say this person is exposed to this pollution. And so again, I'm not trying to claim that any of this is easy, but the kind of link between the exposure we're interested in determining whether somebody's exposed is straightforward. So that's kind of the left side of the slide. The right side of the slide is a different type of problem in causal inference, I would say, where we're interested in the effect of an intervention. And in air pollution, at least, these are sometimes called accountability questions. So for example, instead of saying, what's the causal effect of exposure to air pollution, we might ask, what's the causal effect of some regulatory action, some intervention that occurs? And this is sort of the side of the slide, the kind of class of problems where it's not necessarily as conceptually straightforward to even conceive of how we characterize how a person is exposed to a policy or exposed to an intervention. And in particular in air pollution, this may be really difficult because air pollution moves in time and space. And that's sort of what's going to motivate a lot of the methods development that I've been working on lately. So hopefully this makes at least a little bit of sense to people, this sort of distinction. And I'll dwell on this a little bit more to say, if we're interested in these questions about effects of interventions, there are some interventions that can be cast, analytically at least, in terms of a typical type of epi question, where just the exposure we're interested in is an intervention. Right. So Duncan alluded to some work that I'd done a while back on the, estimating the effects of enforcement of the National Ambient Air Quality Standards, where the policy of interest here is there's this standard, and some parts of the country don't attain the standard, and they have to do something to clean up their air quality. And in a study like that, again, arguably, it's conceptually straightforward to say, well, people who live in an area that's not in attainment with the standard are exposed to this policy of enforcing the standard. Or there's another sort of famous study for those of you in the air pollution world, you probably know this Dublin coal ban study, where they said, okay, we're not selling coal in Dublin anymore for home heating. And then that cleaned up the air in Dublin in a pretty abrupt way. And it's pretty clear that everybody who lives in Dublin was exposed to that citywide coal ban when it went into effect. There's no sort of conceptual difficulty there. And then of course we can think about clinical therapies if we're talking about a treatment. Like a patient receives that treatment or a patient doesn't receive that treatment. And that notion is usually not ambiguous in those types of clinical studies. But the common theme I'm trying to draw out here is, with some interventions, it's pretty self-evident sort of which people or which populations we would regard as being exposed to this intervention and which people we would regard as being not exposed to this intervention. Sometimes this works nicely. And we can cast this as sort of with a similar set of methodologies as we can a sort of more typical epidemiology question about the causal effect of an exposure. But the point I want to make is that's not always the case. So there are some interventions that we might be interested that cannot be cast in terms of these typical epi evaluations. And so I have some examples here. Only some of them have I worked in, so I'm stepping a little bit outside of my depth here. But so picture an intervention that's a smoking ban in public spaces. Well, you're in California, this is old for you, right? But a smoking ban in public spaces. So how do you characterize whether somebody is exposed to a smoking ban in public spaces? Well, it depends on how much time a person spends in those public spaces. If you work in a restaurant, then that smoking ban on restaurants probably has a sort of big impact on your livelihood. If you never go to restaurants, then it probably makes no difference. So there's a much more convoluted link between the intervention and how you would characterize somebody's sort of extent of exposure to that intervention. This is sort of a project that I've been involved into recently. You know, of course, having moved to Texas, you have to do petroleum engineering. There are all these questions about, you know, people have probably heard about fracking and some of the sort of, I'd say, unintended consequences of fracking for oil and natural gas extraction. And there are questions about saying reducing wastewater injection wells at fracking sites, and questions about whether that causes a reduction in the number of earthquakes happening in parts of Oklahoma and Texas and stuff like that. Where you have these point locations where the drilling well is, and you do something in that well, but how any given area's exposure to the action at that fracking well is going to depend on the surrounding geology. Because the implications of drilling a really deep well and filling it with wastewater at a given location, they kind of spill over according to the shape of the earth in that location. And so it's not necessarily clear how to characterize how a population of people or an area will be exposed when you take this action at a point location. It kind of spills over across space according to, in this case, geology. Or a timely thing here, what about vaccine deployment? So this is sort of a common example in these types of questions. If we deploy vaccines into a population, you know, of course, whether I get the vaccine matters in terms of my protection against infection, but who else in my community gets vaccinated, of course, also matters for me. And so you think about things like herd immunity and stuff like that. There's no kind of direct link between kind of a discrete action and a notion of a person's exposure. Like, it all kind of depends on how people are connected to one another. And then the example that I'll stick with for the rest of the talk is this one where you install some emissions control on a power plant, and how that propagates into changing the exposure of populations depends on how air pollution moves through time and space. But again, the point I'm trying to draw out here that I hope we can kind of keep in the back of our minds as we proceed with the talk is that there are these types of problems in public health interventions where the link between the intervention and some change in a person's exposure can be very complicated, and we can't really control it. Anyway, so I'll pause there. As I said, this is sort of the first time I've tried to articulate this in front of an audience, so I don't know if that connected at all or not, but if people have questions, please jump in if you can.
Can I just ask one about your prime example here about emissions controls? Is there not another kind of interference that involves installing emissions on one plant may affect the propensity of other plants
to do it? There is.
Of economics.
Yes, there definitely is. Plants are owned by the same company. They invest in some technology in one plant and crank up their emissions at another plant. Unfortunately, I don't have anything statistical to say about that. This is a problem that I've been, by you, Duncan, and others, encouraged to think about, and we have thought about it, but I don't have anything smart to say about it. But yes, that would be another kind of manifestation of what I'll talk about in a second as interference. Okay. So if what I'm trying to articulate here doesn't resonate with you at all and doesn't make any sense, hopefully it will continue to come clear in the context of this specific power plant example. But this is my preamble. All right. So I'll talk about the specific problem that's been motivating some of my methods work over the past handful of years, and it's evaluating pollution interventions on power plants, coal-powered power plants specifically. So I have some background here on how air pollution is bad for you. I'm mostly going to skip it. I think people probably understand that. And there are people here who know way more about this than I do. But the idea here is we basically know the focus of this talk is really going to be on one type of air pollution called particulate matter of a certain size, fine particulate matter. We sort of know that, you know, from more typical epi investigations, we know from decades of research that this stuff is associated with increased health burden. But then there are a lot of sort of follow-on questions of what can we do about it. So there are lots of regulations in the United States to limit population exposures to air pollution, and at a high level, sort of a lot of my research is trying to figure out ways to evaluate how well these regulations work. But they're wildly expensive and wildly beneficial regulatory interventions by most accounting. So if we talk more specifically about a specific major polluting source, we can talk about coal-fired power plants. And power plants, when they burn, in this case, coal to create electricity, to create energy, they emit lots of stuff into the air. And so that's what this sort of picture is meant to convey. But what's written here in red as secondary PM2.5 is going to turn out to be a very important part of this problem, because, and what that means is lots of chemicals, let's say, come out of the smokestack when coal is burned. But what happens is some of those chemicals start to react with other things in the atmosphere, and they start to blow with the wind, and they don't come out as part PM2.5, but over time and space, they become PM2.5, loosely speaking. Again, there are people here who probably know more about this than I do, but there are various chemical reactions. There's a lot of chemistry and physics that happen, and things that come out as, say, SO2 eventually convert into particles, but this happens over a pretty wide spatial scale. So the stuff that comes out moves. That's really the main point. We'll talk about that a lot. And so the idea is that in order to control emissions from power plants, some of these coal-fired power plants install what are called scrubbers in response to regulations, where you can think of scrubbers as scrubbing the SO2 out of the smoke that comes out of the power plant. The idea being, if these power plants can install these things to reduce their sulfur dioxide, SO2 emissions, then it reduces the secondary formation of this PM2.5, then there's less of those particles in the air, people are exposed to less, and there should be some downstream health benefit. That's sort of the anticipated chain of events here. And so the question that we'll ask in the sort of specific case study I'll get into in a moment here is, does installing scrubbers on these coal-fired power plants causally affect hospitalizations for ischemic heart disease among Medicare beneficiaries? So that's what we're gearing up towards. And so here's a little bit of a cartoon about why this becomes a very, I think, challenging analysis, is because in this cartoon, this yellow triangle is a power plant located in sort of Western Illinois. And what this green trajectory, actually I should ask, can people see my pointer, the arrow? Okay, good. What this green trajectory is supposed to denote is where the air goes once it leaves that power plant. And we'll talk a little bit about where this type of trajectory comes from. But the point is, this gives you an idea of the spatial extent of pollution transport. This stuff comes out of a power plant in Illinois, and people in New York end up breathing it, loosely speaking, right? And so, in principle, anybody who lives along along this green trajectory is exposed to some extent to an intervention that happens at this yellow triangle. So this is a much more complicated sort of scientific phenomenon than just saying, well, do you live near the power plant or don't you? Because this stuff really moves over quite a broad scale. And so, again, in principle, well, I didn't say this, all these black dots are zip code centroids along the trajectory, that band of black dots. So in principle, if we intervene to install a scrubber on this yellow triangle, on this power plant, anybody who lives in one of these zip codes is to some extent exposed to this intervention. And this is the way we're gonna try to make some causal inference progress on this problem is to frame this as being a problem of making inference on a network of interconnected power plants and population locations. And that's what's called, at least in the causal inference literature, interference. I'm gonna skip that part. Okay, so I presume there are, well, I guess I won't presume anything. I'll presume some people here know a lot about potential outcomes. I presume everybody does not know a lot about potential outcomes formalization. So we'll go through some of this. But, oh, I should say, but from the sort of statistical methods angle of this, we've framed this problem that I'm going to talk about as one as bipartite causal inference with interference. So I'll say a little bit about what I mean by that. So the idea here, the defining characteristics of this setting that I'm calling bipartite causal inference with interference, is that we want to evaluate the causal effects of an intervention, in this case a binary intervention, it happens or it doesn't. We want to evaluate the effects of that intervention where we are confronted with something we'll call a bipartite structure here, which means that the intervention we're interested in is defined on one type of observational unit, in this case a power plant, right? Whether a power plant puts a scrubber on or not. And then we're also confronted with a separate type of observational unit where the outcomes that we're interested in are defined and measured on some other type of observational unit. So for example, the hospitalization rate among Medicare beneficiaries at a zip code. So zip codes are not treated with a scrubber, and power plants don't have hospitalization rates. So we have to kind of keep both of these things in our minds at the same time. So that's reminiscent of a bipartite graph, if people know about graphs and stuff. So that's the bipartite structure. And then we're confronted with this other phenomenon where there's interference, which means there's some interconnectedness between the units here, which means that outcomes for any particular unit are going to depend upon treatments that are assigned to multiple other units. There's no sort of one-to-one correspondence here between a treatment and an outcome, because the outcome in any particular zip code is going to depend on what's going on at the whole network of power plants. That's where we're going with this. And so to formalize this, to put some formality to this, there's, we'll layer on a bunch of notation. So the first type of observational unit, the interventional units, these are the power plants. So say we have capital P of these. These are the observational units where there's an intervention that's defined, and we know whether the intervention occurs or it does not occur. And that'll be denoted with A. So AI equal to 1 means the ith power plant has one of these scrubbers. What will become important as we go forward here is we're going to have to think about sort of the individual treatment of a power plant, but also the entire vector of treatment allocations to the entire network of power plants. That's going to be something we have to keep track of. And then we would typically have covariates measured on the interventional units, denoted here with W. So things like the size of the power plant, how old it is, things like that. So the other type of observation units we will call outcome units. So we will have capital M of those. Those will be zip codes in the example. And these are the units on which we measure the outcomes that we're interested in, the health outcomes. So, So YJ will denote the outcome measured at the jth outcome unit, like the rate of hospitalization for ischemic heart disease among Medicare beneficiaries at zip code J. And then we would typically have a different set of covariates noted with X that are measured at the zip codes, population demographics, weather, climate things, stuff like that. So those are the two types of units we got to keep an eye on for this. And so if we start to think about formalizing some of this in terms of potential outcomes, the kind of quote unquote standard setting of potential outcomes notation actually assumes no interference. So this is usually framed in terms of what's called the stable unit treatment value assumption. But again, for those who don't think about potential outcomes every day, the way that we formulate this is we say the potential outcome, like the potential IHD hospitalization rate that would occur at location J, is not a function of the entire vector of treatments, A, it's just a function of the jth unit's treatment. And so this is like kind of motivated, think of a clinical study, whether, whether I respond to whatever therapy my doctor gives me depends on whether I get that therapy. It doesn't depend on whether you get that therapy. So think of like a cancer clinical trial or something. My cancer remission will depend on what chemotherapy I get. It does not depend on what chemotherapy you get. This is kind of the standard setting. And this is actually the assumption that does a lot of the heavy lifting if you're used to thinking about things as saying, oh, so, well, there are two potential outcomes. What would potentially happen if the treatment were there, and what would potentially happen if the treatment were not there? That notion of there being two potential outcomes for every unit is anchored to the stable unit treatment value assumption. But where we're going with this in these sort of network problems and interference problems is that this stable unit treatment value assumption is not an assumption that we want to make. where we will expand things here to say, and at least in full generality, the potential outcome, the potential ischemic heart disease hospitalization rate for the JAIF outcome depends, again, in full generality, on the treatments at all P locations. It depends on all the treatments, not just a single treatment. And so in this case, instead of there just being 2 potential outcomes for each unit, what would happen if the unit were treated and what would happen if the unit were untreated, we have 2 to the P different potential outcomes for each unit. Because in full generality, what happens to that location depends on how we allocate treatments to all the other power plants. And there are P of those, each treated or untreated. So there's this explosion in the problem where we go to from having 2 potential outcomes for each unit to 2 to the P potential outcomes for each unit. And so we've got to put some structure on this in order to make some progress. I'm just curious if, at least for those with your camera on, if you can just give a wave, if you've thought about causal inference with interference before, if this is something anyone's confronted. Mostly not, I would assume. Duncan, yes. Okay. So again, like the main takeaway here is that if the idea of there being, if you're not thinking about causal inference all the time in the course of your own work, right, and you've heard the notion before of there being 2 potential outcomes, what happens if you're treated and what if you're not treated? We're in a setting where the doors are blown off of that simplification because the outcome at any given unit actually depends on the treatments at all the other units. And so we have a much more complicated problem. That's like, I think the main takeaway I'm trying to convey here.
So I guess the vaccination problem would be very similar in that sense because of the concept of herd immunity.
Exactly. Exactly. So, you know, infection risks of a person, you know, you can not get the vaccine, but still have a lot of protection from infection owing to the fact that everyone in your social network got vaccinated. And in fact, the earliest development, I think most of the early development in this type of problem was done in this context of vaccine studies. That's where a lot of these methods grew up, I think. Okay, so let's put just another cartoon to this to try and hammer home the idea. So this is, I always say this is where I used to live. I need to update the slide. But this red dot is a location and a zip code in Boston. And we want to denote the potential ischemic heart disease hospitalization rate that would be observed at that location. And so the question is, well, which power plants need to be inside the parentheses here because they have some impact on the IHD hospitalization rate at that zip code? Is it just the closest power plant? See that little yellow triangle there? Or is it the 10 closest power plants that actually matter? And so using some of the methods we'll get into in a moment, it turns out that intervening at any of these 278 power plants has some bearing on the air quality at that zip code in Boston. So again, just to give you a sense of like what this, like how far this dependence can extend for pollution from power plants. And so in principle, if any of these triangles get intervened upon, there might be some impact in that red dot. And so it actually turns out 48 of those 278 power plants actually had these scrubbers in the year that, I think it's 2005. So again, that's just a cartoon to give an idea of the scale. But the point of interference when you confront it is this phenomenon, it actually introduces some new causal quantities that might be of interest. So the interference is something that's more than just accounting for or addressing the structure. It's tempting, especially in these settings, these air pollution settings, to think of it as being sort of like spatial correlation, but it's not that. It's actually quite different. Spatial correlation, we say we know it's there, we want to account for it in some way in order to estimate the things that we want to estimate. This is a little bit different in that it actually it introduces new quantities, new causal estimates that we might want to estimate that don't make sense if interference is not present. And so as I sort of alluded to, I should change budding because some of this research is getting pretty old now, but most of the research on statistical methods for interference is done in pretty specialized settings. There's a lot in infectious diseases and a lot in social networks because it's a similar idea. You give me some educational intervention to say, get me to stop smoking, and I'm friends with you, and I tell you about that intervention, and it makes you more likely to stop smoking. All kinds of these, and think about how companies like Facebook are intervening to change spread of information across Facebook friends networks and stuff. It comes up all the time in social networks and infectious diseases. But the point here, and this is just a quote from a paper by Eric Checkin and Tyler Vanderweel, who are sort of among the pioneers in this area, is that interference is not simply a problem that needs to be addressed. It actually gives rise to new causal quantities of interest. So just to tell you, I didn't make that up.
Cory?
Yeah.
Sorry to interrupt you, but just a quick question. Are you sort of, the way you're framing it or thinking about it, are you thinking to sort of like, you know, accounting for dynamic feedback loops types of things, or just figuring it out in a static way?
Well, that's a very good question, because what I'm going to end up doing is treating it all as kind of static. Not so much static, but kind of like summarized over a set time interval.
Got it.
In reality, this is a dynamic thing. I'll try and get to that when we get to the air pollution things. But in principle, it could be either. I'm not sure the sort of statistical methods have quite caught up to where you have social network evolving over time.
I wouldn't even know how to deal with it. I just wanted to understand how you're thinking about it. Thanks.
For the purposes of this talk, we can think of it as the social network, or the network, what we'll talk about, is sort of a static thing.
Okay, thank you.
That's a great question. I keep looking over here, even though I know my camera's here, sorry. All right, so just a few notes on what the notation looks like. And my hope is that we don't need to like dive super deep into the notation to make sure we know what's going on here, because it's dense, as you can see. But we'll at least breeze through some of it. So in terms of writing the potential outcomes, remember, for the jth zip code, we'll write the potential outcome as a function of the treatments assigned to all P power plants, this entire vector, where the ith element of this treatment vector is the treatment assigned to the ith power plant. And we'll use this notation A minus I, vector A minus I, to denote the vector of treatment assignments at all the power plants except the ith one. So this is going to come up in some of the notation too. And so we can think, just to kind of hopefully build up some intuition about where we're going to go with this, is the most primitive sort of individual level causal effect we can define, and we can't estimate this, but just conceptually that we can define, is to compare the potential outcomes at location J under two scenarios. The set scenario where there's a treatment allocation where the ith power plant gets treated with level A, and there's a particular assignment vector to all the other power plants, and compare what would happen under that scenario to some other scenario where the treatment assignment to the ith power plant is some other A prime, and the treatment vector to the other power plants is some other bold-faced A prime. So this is, again, to put this into words, the effect on outcome unit MJ of treatment allocation with A having AI equal A versus treatment allocation with A prime having AI prime equal to A prime. Sounds ridiculous to say it, but hopefully for those of you used to this type of notation, you can see what this is getting at. But the key point I want to make here, that's owing to the bipartite part of the problem, is that for every location, for every J, we can define P of these effects, because which power plant we're calling out and separating out from the vector can change. So we could say that at location number 1, the effect where power plant number 1 is treated with A and blah, blah, blah. Then we can write at treatment location 1 where power plant 2 is treated with A and the others are blah, blah, blah. And then treatment location 1 in power plant 3, and so on and so forth. So for every J, we can define something like this for every I. And so another way to put this is to say we don't have an obvious notion of saying that any treatment at any particular I is sort of the direct treatment on location J.
Now I'm confused, because it looks like if you want the effective treatment on power plant I, you're allowing all of the others to change at the same time.
You could. In full generality, you could. But maybe this will be more clear when we see what we're actually trying to estimate. But the point is, even if you fix, let's say you fixed these, well, we'll get there, Duncan, actually. Hopefully I'll clarify that in a second. But the point I'm trying to make here is just simply, if you just look at the indices here, for every j, you can change the value of I and always be talking about something about the effect of power plant I on location j, and then the effect of power plant I prime on location j, and then the effect of power plant I prime prime on location j, for example. So this is getting more to what I think Duncan was just alluding to here, is we can define different types of effects, or which I'll refer to as mostly as direct and indirect effects. So there's something called a direct effect, which gets at this notion that I think Duncan was just alluding to, where we say, what is the effect of treating the ith power plant versus not treating the ith power plant, while holding fixed the treatment allocations to all the other power plants? So that would be something like a direct effect. So again, in words, the effect on location j of intervening versus not on power plant I under a given a fixed allocation to all the other plants. This would be like a direct effect. But again, this is indexed by I and j. So we could power plant I, and then we can go to a different power plant and conceive of it for that one. In some sense, the flip side of that is the indirect effect, where here we say, assuming the ith power plant is not treated, what's the effect of changing the treatment allocation strategy to the other power plants from A to A prime? So this would, you could think of this as saying, what's the effect of changing scrubber installations at all the upwind power plants, but keeping the ith one fixed? Is that, and this, I fixed the ith one at 0, you could fix it to 1 also.
But then I don't see how this is an indirect effect of I, because there's no change in I.
It's the indirect effect of treatment at the not I.
Yes.
But I think that part of what's a little bit awkward about this is direct and indirect don't really mean anything in this bipartite network, because you don't directly intervene on any of the outcome units. And this is like kind of one of the big differences. I didn't say this. I thought I had it in the slide. I mean, there are two, I'd say, kind of things that complicate the methods problem that we're trying to address here. One is the notion of interference. The other is the notion of this bipartite structure. So these two things don't need to appear together. They just appear together in problems I've been working on. So the terminology of direct and indirect effect, you think of it in a vaccine study, where you don't have this bipartite structure. All you have is people in a network, and some of them get the vaccine and some of them don't. And so the direct effect would be like the effect of giving this person a vaccine versus not, while holding fixed whatever, the vaccine statuses of their family. And the indirect effect would be something like not giving this person the vaccine, but vaccinating everyone in their family versus not. And when you have this correspondence between which treatments directly apply to a unit and which treatments indirectly apply to a unit, this terminology makes a lot more sense. If we're in this power plant zip code bipartite setting, the terminology is awkward. So I'll switch it up in a second. But if anyone happens to follow this literature, this is usually what these things are called. So with all those things I just defined on the previous slide, one of the points I want to make here is they're all defined for every IJ combination. And because of what I've just been talking about, there's no self-evident meaning of an intervention applying directly to any outcome unit here. You don't treat a zip code with a scrub. And so we've done a variety of things in this setting, but one of the things we've done is focus attention on what we call a key associated causal effect. And the idea is this: consider for each J, so for each zip code, consider that we can identify a single power plant of sort of primary interest. So for example, the closest power plant to that zip code. Or maybe sort of geographic proximity is not the thing, but it's some other measure of the power plant that has the most influence on that zip code. And we're going to denote that with I star. It's a sort of abusive notation, but I think it'll be clear. So what that says is, even though all of these things are technically defined for every IJ pair, for every location J, we're just going to focus on one IJ pair. we're going to focus on the one corresponding to this I star. And so now we can think about, as I thought I had it, so we can think about this notion of a direct effect as being what's the effect of treating versus not the I starth power plant, the most influential power plant, while holding fixed the treatment statuses of all the other power plants.
Mhm.
That's what we're going to go with this. Okay. Anything else on people's minds before I keep moving on that we should stop and talk about?
I have a question here.
Yeah.
So I totally don't understand.
I don't want to belabor the point, but
don't know much about.
sorry,
Oh.
Sean, are you speaking?
Yes.
Go ahead.
Yeah.
Oh, okay. So so as a newbie in totally outside this field, I guess you have a bipartite structure with power plants on the left and zip code on the right, and we know the exposures are really more or less like collective exposures.
Right.
In other words, there's something hidden, a layer of hidden variable to have an impact. So I guess my question has two aspects of it. One would be, is it still fair in this situation to ask the question of causal effect of an individual power plant? And two, two is, if the answer to the first question is partially no, whether we should think about explicitly modeling the intermediate layer.
Yeah. Great questions. So the answer to your first question is yes, it is fair to, it's not the only thing you might want to do, but I would argue among the things you might want to do is be interested in questions that are about specific actions that occur or not at specific power plants. So, and that's like kind of what motivated at least these statistical methods. There are other questions, but you are also, I think, right to think about it as like there's some latent exposure here, right? Whatever happens at the power plants generates some exposure. And might we want to just answer questions about the effect of that exposure and just not worry about the links back to individual power plants? I think maybe that's what you were getting at with the, maybe I'm mischaracterizing. But what I would say is we might want to do both of those things. And in fact, we have done both of those things.
Okay.
To your second question about what do we want to do to model this process, like to get at this thing that seems like a latent quantity, that's what I'm about to talk about in a moment. Because in this problem, that is exactly how we're going to approach it. We're going to find some way to characterize the mechanics of how air goes from this power plant and blows over here so that those people breathe it. And that is not always how these problems are solved, but it is how I think they should be solved in problems like this, and for reasons I'll talk about in a minute. They're great questions. Did you have something else, Duncan?
Well, I was just thinking in the language of mediation, I would think of an indirect effect as the effect of holding the effect, the status of power plant I fixed.
Yeah.
What would be the effect of AI minus prime being what happens to all of the other power plants if one were to change I? And that's getting back to the economic question that I asked earlier. If I were to intervene on plant I, what would be the effect on all of the other plants' behaviors?
Yeah, so for one thing, this is part of why they are called indirect effects, is because the sort of analog to mediation is real, and if we had a chalkboard, I could show you, right? Okay. And it is kind of like the indirect effect is a little bit like it's a little bit like the effect on the ith unit that's mediated through the neighbors, like mediated through the other connected units in the network.
Right.
And there's an analog there. So that, I think your sort of thought or your instinct there is right. As for the part about whether, there's nothing in the methodology I'm about to present that would acknowledge the likely reality in this case that when you intervene on I, you actually are likely to, you can't just intervene on a single I. Because if you were to actually intervene on an I, some I prime would change its treatment because of the economic things like you said. So what I'm going to present, there's not an obvious way to get that layer of complexity, or at least we've not done it. So you can think of everything I'm going to present in terms of the methods we have done. It kind of assumes implicitly that that doesn't happen. It relies on some implicit or explicit assumptions about how, like, being able to conceive of intervening on I and nothing else, which may be a stretch, depends on the context. Anything else on people's minds? Oh man, I'm way behind here. I've been blabbing on, so I got to wrap this up. Okay. You see, I only have, 30 more slides. So let me just talk a little bit. I will pontificate a little bit about the question. I think sort of what Chun was getting at here is, so what do we do in order to model this process? And so usually when we're talking about interference, it typically arises from sort of unit to unit outcome dependencies. Like, I get a vaccine, I'm less likely to get infected, and therefore I'm friends with you and I am less likely to infect you. That's usually the case when we're talking about social networks or infectious diseases. But here we clearly have a different type of a process where these interventions on a network, and they spread across the network according to, in this case, some physical chemical process. And so the question is, how do we learn about that process? And we've kind of pursued two different things in my work. One is what I'll call the engineering approach, which is basically say we collaborate with atmospheric scientists and we basically say, tell us about the physics here. And so we can come up with a way to say, when we put a scrubber here, which populations are going to be impacted. And so we've developed a lot of methods there, which I won't really talk about. And then we've also pursued some like purely statistical approaches to say, well, we've got, the statistician in me when I started with this said, well, we've got a lot of data on the emissions from power plants. We've got a lot of data on the air pollution all over the place. Like, we should be able to do this. We should be able to learn that if emissions go up here, air pollution goes up there. And I at least Rima's probably smiling at the comment there. Engineers will think you're crazy. And I've been laughed out of many rooms with engineers saying it's way too complicated. You can never do this with statistics. You need a chemical transport model. And good thing I never listened to them, because I think we've come up with some useful things. But anyway, that's a whole separate talk about like collaborative science that I also think would be interesting. But that's not what we're here for. But what I'm going to actually show you now is more or less, I mean, in reality, do we want to do a statistical approach or an engineering approach? We probably want to land somewhere that's a combination of the two of these things. And I'm going to give you, we sort of made the most progress so far in something that I think is probably a little bit closer to an engineering approach. And so I won't say exactly how we did this, other than to say that, remember this cartoon with the trajectory? We more or less came up with a very computationally scalable way to do this. And if there were more engineers here, we could explain the details of how that works. But you'll just have to take my word for it. So what do we do here? What we actually do here is we take this complicated network, and we have some measure now of the network structure, the sort of latent structure of which power plant is connected to which zip code. And we formulate the problem as one of a bivariate treatment. So we define what can be regarded as like an individual level treatment, which will be whether or not the key associated power plant has a scrubber. And then we conceive of something that's called a neighborhood level treatment, which is like some function of the treatments of the neighbors in the network, of like the upwind power plants. And that's what's going to allow us to make progress on this problem. So I'll skip through the sort of how exactly we do that in any detail. But for the individual treatment, what we do is we use the output from one of these sort of approximate atmospheric physical models to say, for every zip code, let's identify the power plant that has the most influence on the air here. We'll call that the key associated power plant. And we'll call AI star to denote whether that key associated power plant has a scrubber or not. And then what we do is we calculate what I'll call an upwind treatment, which is a function of the treatments applied at all the power plants who are blowing their air down to a location. And so without going into any of the detail, it's this function that I'll call G, which is sort of like a weighted average with weights corresponding to the output from this physical model, if that makes any sense. But now we have this sort of bivariate quantity for every zip code. We have whether its key associated power plant was treated, and then we have some function of the treatment statuses of all the -I other power plants. And when we do that, we then can deploy some methodology based off generalized propensity scores to try and estimate some things that are like direct and indirect effects. So let me just show everyone what this looks like when we actually deployed it in an analysis like this. So just to give a sense of the data, we have data in 2005 for 472 coal-fired power plants in operation, and about 100 of them had one of these scrubbers installed. We also have data on about almost 24,000 zip codes, and we're only going to use a subset of zip codes where power plant pollution is actually that. Coal power plant pollution is actually there. Like in California, you don't have coal-fired power plants anymore, so you don't have a lot of coal-fired power plant pollution, so it doesn't make that much sense to talk about this problem in much of the Western US. Most of the coal generation is over here. Anyway, so we have about 24,000 zip codes, and we want to know how putting scrubbers on these triangles affects IHD at these zip codes. And so just to give you a map here of the zip codes, the yellow colors on this map are zip codes where the key associated power plant has a scrubber, and the purple ones are the power plants where the key associated power plant does not have a scrubber. And the white ones are zip codes that are omitted from the analysis for reasons related to propensity score overlap, which I'm happy to talk about if folks are interested in. What we actually do is we estimate something that's like that's what we call a joint propensity score. Remember, we have this bivariate treatment. So if you've thought about propensity scores before, it's the same idea, except it's a propensity score where we don't have a single, it's a propensity to receive treatment, where treatment is a bivariate quantity corresponding to A and G. And so we decompose it in a particular way to come up with something we call an individual propensity score and something we call an upwind propensity score. But once we do that, we can more or less deploy these quantities in ways that propensity scores have been used in lots of different contexts. So if you've heard of propensity score matching, subclassification, inverse weighting, or whatever, we can do things like that now with these quantities. There are unconfoundedness assumptions that are a little complicated here. This is actually a simplified version of what we actually have to assume. But the point is here that in order to try and adjust for confounding in a problem like this, we have lots of data on the power plants, lots of data on the zip codes, and some data on weather, basically, humidity, temperature, rainfall, stuff like that. And so the estimation strategy looks something like this. We estimate the sort of propensity for a zip code to have its key associated unit treated. And we do this in a pretty simplistic way. It's just logistic regression as a function of a bunch of covariates. Then we stratify all of those 24,000 zip codes into 5 categories based on the estimated propensity score. That's sort of a standard approach with propensity score adjustment. Then within each of those K strata, or those 5 strata, we estimate this other element of the propensity score that we call the upwind propensity score. And then we end up adjusting for this propensity score in a very simple parametric Poisson regression model. And so the details of how the estimation works are not that interesting. I think the key takeaway is we have this joint propensity score. We define these 2 components of the joint propensity score. And then we kind of slice and dice these zip codes according to the value of these 2 propensity scores in order to adjust for confounding. What we get at the end of the day here, you know what, I forgot to, oh no, that looks like it might be right. This is like an estimate of the dose response function for putting more scrubbers upwind of a location. So if we look on the left, this is saying for locations where the key associated power plant, for locations where the key associated power plant does not have a treatment, that's the 0. This is like a dose response function for putting more scrubbers upwind. And so we see that it decreases here, and then it sort of flattens out, and then the uncertainty kind of blows up. So most of the data is over here. So what we sort of see is that it looks as though for locations where the key associated power plant does not have a scrubber, there are reduced IHD hospitalizations as there are more scrubbers put upwind. And we get a very similar picture over here as well. If we put some numbers to it, I don't remember whether I updated these, but we say that we get something like an average direct effect to say the average direct effect of installing the scrubber on the key associated power plant is a reduction of about 8 hospitalizations per 10,000 person years at that zip code. And then we can also say, what's the average upwind effect of installing more scrubbers on the upwind power plants? Oops. And we see that it's a little different, maybe depending on whether the key associated power plant has a scrubber. But we basically see on average, it looks like putting more scrubbers upwind reduces the IHD hospitalization at that given location. That's what these last set of bullet points say. Boy, I don't know. So I guess I'll leave it there and just say that we have this class of interventions in public health and air pollution, certainly, where we have to confront this problem that when you let us down on this network, and they don't just act locally, they kind of spill across the network. In air pollution, they spill across time and space. But some of you may be able to imagine settings like this in other areas that you work in. I didn't say much about this, but a lot of the work underlying here was a lot of very interdisciplinary work, I think, that was really combining some rigorous statistics with, I think, some smart atmospheric science to try and make some progress in a problem like this. And I think there's relevance to perspectives like this in other types of interventions where it's more appropriate to think about them as sort of diffusing across some network, in particular, when you know something about that diffusion process. Like we know about physics and chemistry for air pollution, so we can get some traction on how that happens. So I'll stop there. Yeah, sorry for sort of rambling about some of that stuff and skipping over some of the more statistical stuff. I didn't mean to do that, but.
Well, Cory, thank you very much. In fact, I don't think it was because you were rambling. We had a lot of questions for you.
Okay, thanks. Okay.
And to remind anybody that showed up late, we're going to just start having questions now, and Cory is willing to hang around for another, I don't know, hour or so. So those of you that are really motivated and would like to hear more are welcome to stay on, and I'll keep the Zoom open as long as we need. But that'll give you a chance, Cory, to back up and go over some things that you felt like you might have.
I mean, if folks want to talk about it, I'm happy to.
But let's hear if there's some questions first.
I have a question again.
Yeah.
This is probably a typical statistician question. It may not have a real impact. So your analysis, I think, is the unit of analysis is zip code, and we know there's a population density. Because of that difference in population density, and because of that, some zip code may cover a small area, some cover a big area.
Yeah.
So in your data, you essentially have a somewhat overrepresentation of dense area, and less representation of relatively less representation of the less dense area. So that would lead to this data correlation issue. Some data are more correlated than some others. I don't know whether that would have a big impact in your analysis or not.
Well, I guess I'm not sure I exactly know what you mean. So We do, I mean, you are certainly right that some zip codes are large and have small populations, some are small and have large populations. There's a lot of variability there. And because a zip code is a geographical area. But, so we have rates like counts and denominators for each zip code. So there's nothing about the sort of analysis of the outcome that, you know, doesn't account for the fact that you're much more certain about the IHD hospitalization rate in a zip code with lots of people than you would be in a very rural area where there are not lots of people. But, oh, go on.
Let me just elaborate a little bit more on the my question. So I'm not asking from the perspective of standardizing or normalizing based on the population size per zip code. I'm asking from the perspective of, you know, if you look at the exposure, the pollution, if you have a luxury of collecting data from this big eastern area of United States, you would want to collect the data in an even way, like, you know, the result per square mile or something like that.
Yes.
But now your zip code is not per square mile. Some zip code is just, you know, a few square miles, some maybe.
That's right. Yes, okay.
So I'm thinking from that perspective.
Yes.
So you have an oversampling of certain geographic area and undersampling of certain other geographic area.
I see. No, I mean, I understand. I when it comes to the, let's see if I have a pic, well, I guess it doesn't really matter what picture I have. So when we calculate the quantities that are going to end up making this exposure, it is calculated on a like per, it's not per square mile, but a like sort of common spatial unit. So we actually, what we end up doing is when we calculate this, when we use this model to characterize the exposure from a set of power plants, that exposure is created over like a 1 by 1 kilometer grid across the whole country. And then it becomes a spatial alignment so you can think, so there's no sort of error induced by the exposure characterization by the size of the zip code at that stage. Then what we do is we take a grid, very fine spatial grid, and then there's this kind of, you know, this like GIS problem with the spatial misalignment of the grids to the zip codes. And there are different things you can do there. I shouldn't try to describe what we did here because I'm not the one who actually did it and I'll get it wrong. But how you take that kind of per square kilometer unit exposure and aggregate it to the zip code accounts for the fact that some of these zip codes are huge, like in the middle of the US, and some of these zip codes are tiny, like in New York City. And it's a very good question, and it should do that in a way that does not induce, I think, the type of like potential for bias that you have in mind.
I actually don't know whether there's a bias. I just feel there's some oversampling in certain area and undersampling in certain other area.
Well, that's definitely true in terms of the population. Yeah, I mean that is true. I mean, so you know, the oversampling, it shouldn't be like any bias in estimate of the exposure, but there's a lot more representation in these analyses for the people who live in the Northeast than there is who people live in the Midwest. Like that's just how the people are distributed. And so you can get, if you think about sort of sensitivity of the results to the model, it might be very sensitive to assumptions you make about the spatial process up here, like between Washington, D.C. and Boston, and not that sensitive to assumptions you make about the process over here in like northern Texas. And so there are certainly issues with the kind of uneven distribution of the people and the exposures in space.
Okay, thank you.
Hi, Cory, this is you. Actually, I do run the interference issue when I studied infection disease. So I think I understand your note very well, but I do have a question. So in my interference study, typically I assume the intervention, like the patient I received, is independent with the intervention patient J received.
Right.
But in your case, apparently this is not the case, right? In other words, the since you so actually the thing I got a little bit confused by in your note is, like, let's say we have only two power plants, A1 and A2. Okay. In the potential outcome framework, the outcome is a function of A1 and A2. And in the standard interference literature, we assume the AN and A2 are independent. But in your case, this A1, A2 could be highly dependent, like Duncan said. If the A1, A2, the plant A and plant 1 and plant 2 come from the same company, they may install the scrubber at the same time. In other words, the possible value for the exposure matrix is either 1, 1 or 0, 0.
Right.
So I think in that case, it's hard for me to understand how you construct the direct effect, because you only have two possible combinations, 1, 1, 0, 0. You cannot evaluate the contrast between 1, 0, 0, 0, right? Or 0, 1, 0, 0, something like that. So, could you? So I think there's some very. So essentially, my question is, do you think this the assumption about uncorrelated plant power plant is too strong to be true in the framework?
Yeah. That's a great question. Yeah, so that is, so Duncan was alluding to a similar point right at the beginning.
Right.
And you put it very well. Is that assumption too strong? Yes, because we more or less know that there is at least some correlation among the A's. It's probably negative correlation actually between companies that own the same power plants. But
right.
Doesn't matter. So your point stands, right? So something about, and we have in some other methods, we've pointed a little bit towards how you might account for some of that spatial correlation, but nothing that really takes head on the point of whether the estimands actually make sense, right? Because you are right, in this extreme example that you've described, there's no information to estimate some of these causal estimands that I'm calling indirect effects or direct effects, right?
Right.
My instinct with this problem is that, yes, the assumption of no correlation among the A's is too strong. I don't think it's way too strong.
Okay.
So it's like, yes, you are right, but the correlation among the A's, I don't think it's that strong.
Well, I may have missed something here, but where you define your second propensity score for upwind
Yeah.
effect, does that not actually address this question?
Well, what I don't.
Maybe you could put up that propensity score again.
I don't know if this part of it is useful to look at. So the upwind propensity score here is the conditional probability of this like neighborhood weighted treatment G, given these other things, right? It does not, what this would account for, is designed to account for, I think, is the fact that different areas, different locations would tend to have more or less upwind treatments. There are some types of areas where lots of the upwind power plants are treated, and other types of areas where not that many of the upwind power plants are treated. I don't think it would necessarily account for this problem that Yue is talking about, where in reality, in the extreme case, we know that whenever power plant I puts on a scrubber, our power plant I prime doesn't.
Right.
In a standard regression problem, you know, if you're regressing y on x, it doesn't really matter whether x is random or correlated, not in terms of bias. In terms of power, it will, but not in terms of bias of the estimates.
I think that that's right. Not in terms of like bias of the estimates of the regression equation, right? There's an added step here that I breezed over, which maybe I can go to it if I see if it makes sense. There's an added step here where we have something like a regression equation that's conditional on this G and conditional on this, or conditional on these two elements of the propensity score. They're called lambda and phi. But so we have something that's like a regression equation here that's conditional on this lambda. That's like that upwind propensity score. But then there's an extra step where we take the regression coefficients here and predict from it to get these individual potential outcomes, and then calculate some of these causal estimands like direct and indirect effects, things like this. And I think the issue here, like, so in Yue's extreme example, I can write down this causal effect all I want, but I know it doesn't make any sense in that extreme example because you never have the setting where one power plant is treated and the other one is not. And you kind of need that variability across the treatments in order to have a quantity like this make any sense. And so I think that there's a problem, that maybe it's not that big a problem in terms of the estimation of some of these intermediate models, but it may be a problem in terms of like the underlying estimands that are defined.
Yeah.
And like whether they actually correspond to anything that is a reasonable approximation to the problem that we want to study. And so in that extreme example with two power plants, I could do exactly what I have on the slide and estimate an indirect effect, but for the reasons Yue explained, like that indirect effect wouldn't actually make any sense.
Right. That's actually my major concern about this approach. And also, I feel that the bipartite structure is very smart, but I can't reframe. So you essentially create the term called bipartite structure and interference, but I feel this structure can be translated into a scenario where the people have multiple correlated exposure, like multiple exposure issue. Do you think these two things are equivalent statistically?
Equivalent, I don't think so. So I think when you're confronted with this bipartite structure, which actually comes up in all kinds of studies, think of like in education, you have students within schools and there's an intervention in school, but you're interested in the student outcome. So that would be another example, right?
Right.
So when you're confronted with these types of structure, there are many different directions you could go. And we outline this in one of the, I don't know if I listed the references there, but in one of the papers we've written on this, we try to outline this. One of the directions you could go is say, well, I've got my unit of type A and my unit of type B in my bipartite structure. But I could project all of this into just units of type B.
Yeah.
Where like for every, in this case, like for every zip code, you have some projected treatment that's a function of everything else, all the power.
Yeah. Right.
And we have written papers that are more in the epi literature that basically do that. And then once you do that, like it's not even necessarily true that you have an interference problem anymore. You just have every unit has an exposure.
Exactly. Right.
And so we have papers that are published in epi and in epi journals that do that, where they basically say they use this network, and what you end up with is for every zip code, you get some measure that's sort of like a cumulative measure of emissions exposure from all the power plants.
Right.
And then estimate the effects of that cumulative emissions exposure. And so we have done that. And sort of analytically, if you can get that cumulative exposure at the zip code level, analytically, it's a much, much simpler problem to then estimate the effect of that exposure.
Right.
And we've done, well, it doesn't matter what we've done, right? But we've tried to do that. what motivated the sort of methods development in this work is we really didn't want to lose sight of this notion of the discrete intervention that either occurs or doesn't. Because we wanted to make an inference about the effect of that discrete intervention, the scrubber going on or the scrubber not going on. And if you want to maintain that, if you want a causal estimand that's anchored to whether this thing happens or it doesn't happen at the power plant, then it's much harder to kind of collapse the bipartite structure into a single one. We actually kind of end up doing that by defining key associated plant and then this function of the upwind plants. But it's, I think it's a little bit more complicated. And so I think maybe one way to put it is there's a difference between whether you're interested in the causal effect of the cumulative exposure from power plants, or you're interested in the causal effect of this scrubber going in or not. You would address those questions in different ways.
Okay, but I think if we treat as, like you said, project to all single unit, like in this case, zip code unit analysis, and treat each power plant as a specific source of intervention. But I think under this structure, we can allow the correlation among different sources of intervention easily. But in here, when you're talking about the interference, based on my current experience, we typically assume the different AI are independent. So that's why I feel it's there's a trade between these two pros in terms of the assumption we made.
Definitely trade. I agree. I think that's well put. There is a trade-off.
Right.
Do I want to maintain? Do I want to keep my hand on this sort of binary notion of did the power plant have it or not? Or am I comfortable projecting this into some other kind of like summary quantity across all the power plants, like the number of power plants that treated this zip code or something?
Right.
There are real trade-offs there. What we, and sort of as I said, we've kind of tried to approach this problem from both ways. The methods project here sort of assumes that you don't want to give up on this sort of the interpretation around is the scrubber there or is it not for an individual power plant. But you're right. But you're right. And yeah.
Right. Okay. I have two more questions. Sorry. Sorry for so many questions. So I want to understand your upwind effect G notation. Yes. So if I understand correctly, statistically, essentially this is a kind of a dimension reduction technology, right? So essentially you aggregate all the other power plant status into one single metric, which you call G. Is that the idea behind this upper wind effect?
That's right.
Okay.
So, or to put it another way, as you were talking about before, you know, we do end up kind of taking the bipartite network and projecting it onto just the zip codes.
Right.
But it's like a bivariate projection. That is, the treatment of the I star is one part of it, and then the other part of it is this function of all the other treatment.
Right. Great. Okay, that's all into the literature I'm familiar with. I remember there's a very famous paper from just I think it's the author is called Huang. First author is Hong or Hong. I forgot the first name.
Raudenbush.
Right. And they use a similar idea, which is very smart.
Yeah.
And also the last question I have is the covariate unmeasured confounder issue. Did you try to do some sensitivity analysis to see whether your result is sensitive to some unmeasured confounding? Or
nothing formal.
Okay.
Not yet. Not yet. This is a very tricky problem. So no, the answer to your question is no. That's something that we need to think about how best to do in this setting. We've done some very informal things. It's a thorny problem. I don't know if you can really tell here. That's a little bit hard. But here you have this bivariate treatment. There's a very particular spatial patterning to this G. There's spatial correlation between this A star and the G, and that it's very spatially correlated with some of the other things you would want to adjust for. And so that when I show the actual models we used here, which again I didn't really talk about, they are painfully simple models, like just plain old Poisson regression here. And the reason that we did the very painfully simple models is because when we were trying more sophisticated, flexible things, the results are very sensitive. Confounding here is strong. There's a lot of like spatial correlation among the covariates. And what that produces then is you try to do something really flexible and it's not very robust to the model specification. So we kept kind of reverting back to something that was intentionally very simple.
Yeah.
And kind of figuring out the ins. So you know, we did all this work to formalize this problem in this way that required some new development and everything. And then where the rubber hits the road, we do this really simple estimation thing. And what we have ongoing is to come up with a better way to do the estimation, basically, that would really confront some of those problems. So that's all to say we've not done any formal sensitivity analysis to unmeasured confounding, although I think the threat of unmeasured confounding in this type of study is pretty high. And we have to figure out even the observed confounding, we have to figure out better things to do.
Yeah. Thank you. Yeah.
I'm thinking about introducing a change of subject, but before I do that, let me ask whether there's any other questions related to this air pollution story.
Yeah,
Well,
I do have one.
Sorry, 1 second, just to respond to something you said before I forget. A lot of the methodology that I just described, because you work in this area, I don't know if you know this paper that I've highlighted here. This is an old slide. This is the archive version. This is, I think maybe it's appeared in JASA by now, 2020, or maybe it's just on the website. And two of these people, Fabrizio Miali and Laura Frostieri, are working with me on this power plant study that I presented. But a lot of the ideas about the bivariate propensity score and the sort of neighborhood and individual level treatment are developed in a lot more detail in their paper.
Okay.
What we're doing in the work that I just presented uses that as a very robust starting point to say, okay, now let's kind of deal with the bipartite part and apply it in a new setting. But that paper is published, and so I'll draw your attention there. It's a good one. Anyway,
Okay.
sorry.
Good. Thank you. Thank you so much.
Dan, go ahead.
Well, I just had kind of a general comment, but, you know, trying to wrestle with what questions are people interested in asking about this. And, you know, an obvious one is what happens if you require scrubbers to be put on all remaining power plants. And you'd like to predict the effect in terms of the total reduction in the amount of hospitalization or the rate of hospitalization.
Yeah.
And your problem is that you don't have any, all you have is observational data.
Right.
And in no case do you have all of the, an example where you have all of the scrubbers on and then off or something like that.
Right.
Yeah. I mean, is that the kind of problem that you're trying to grapple with in terms of the practicality, the practical issues?
What's closer is a similar variation. No, that is not the type of problem that we're trying to grapple with this. Just because of the way the regulations at least have worked historically in power plants, is the way they tend to work is no entity says you power plant put on a scrubber. You know, there was cap and trade for a while. There's like all these other incentives, and a scrubber is kind of among the things the power plant could do. And if you look in the news, like now they're closing power plants or they're burning different types of coal. So there's always kind of a variety of things that a power plant could do. And the idea of sort of what would happen if you just got rid of all the coal-fired power plants is not the type of question that we sought out to answer. something that I think is related to that and suffers from the exact same problem, that like you don't have any representation in the data to learn about a particular setting of interest, is we get asked all the time if we could use these methods to estimate, to like say, okay, I have money to put on one more scrubber, where should I put it? Like which power plant should I install this scrubber on? These methods are not designed to do that either. And if they were designed to do that, if it were designed to maintain this sort of like individual prediction between acting on this part of the network and the effects on that part of the network, then if we thought we could do that really well, then we might believe that we could predict this like completely counterfactual setting with no power plants, no coal-fired power plants. We can't do that with the methods we've developed. These are really designed to estimate these kind of like average summaries, like on average what happens when you put a scrubber on the closest power plant to a location. And in some ways it's unappealing because that's not always what you want to know. What you might want to know is, should we put scrubbers on all these power plants? Or which plant should we put scrubbers on? And this methodology is not designed to do that. And so it's like how do I put this? It's designed to answer a kind of subset of questions for which you do have the type of variability in the observed data to get this comparison that you want. Whereas the question you described, as you said, you don't have any variability in the observed data between, like, you don't have any representation of what would happen with zero scrubbers.
Right. You have some data, and then you can make some assumptions and things like that.
Yeah, and in this case, it would have to be some statistical assumptions and then also assumptions about the chemistry and physics and stuff. And so maybe we could do that, but these methods are not.
Yeah, I was just trying to get a grip on what kind of problem you're really trying to address.
Yeah, I think that the problem that this is more designed to address, and I've been, make sure Duncan hears this, Brian Hubble insists that this is relevant. He's a guy at EPA who Duncan and I know. Is what this is giving us a notion of is it doesn't say anything specific about any individual power plant, but there's this general notion of, do you get more bang for your buck by acting locally at like what's close by, or spreading actions out, upwind? That's the type of question that this method tries to answer. And people in the policy offices at EPA think this type of thing is relevant because of how they have to write policy. Because downwind states are always suing upwind states and things like this. It's like very much a part of how policy works.
And you have to make, it basically must be using transport models and things like that.
Yeah, so the way engineers...
And ignoring health data at all.
And what?
Ignoring or greatly simplifying any of the health data.
That's exactly right. So like the typical health impact assessment approach that we were trying to, provide a different perspective on than what's usual, is you take a team of engineers, they spend many months simulating with their model, their transport model, what would the air pollution look like if we shut off all the coal-fired power plants? And they get some prediction of what they think that would look like. It's based entirely on their understanding of the physics and the chemistry, right? There's no real data in that prediction. They just take their model and they set the inputs to be zero emissions at every power plant. And they get this counterfactual prediction of what the air pollution would look like with no power plants. And then they compare that pollution surface against like the observed one, and you get like a delta pollution, right? How much lower would the pollution, do we predict the pollution would be if you shut off all the coal-fired power plants? And then, and this is the part that I think you got exactly right, the health data part is completely simplified. Then the way they would estimate the health benefit of that is they'd reach into the epi literature and say, well, we know that a 1 unit reduction in PM is associated with a relative risk of whatever, and they would multiply it by this delta pollution they get from their atmospheric chemistry model. And is that a bad thing to do? I don't think so, right? If you need to make a prospective prediction about what you think might happen, like this is a perfectly reasonable way to do it. But from a statistical perspective, it's like it's not that satisfying because of how simplistic the sort of use of the health data, or not even use of the health data, use of like a published relative risk is.
Thanks for that summary. That was helpful.
So for what it's worth, I put the link to the Forestier paper in the chat.
It's on the JASA website. You found it?
Yeah, I found it.
Good. Oh, my chat's not open.
Cory, if I may change the subject, at least
Sure.
temporarily, some of us are thinking about applications in other areas, and one that comes to mind is COVID.
Yeah.
And I just wanted to pick your brains about whether or not you've given any thought to completely different areas of application, and in particular, whether you've thought at all about COVID.
That's a great question. So I have given thought to different areas of application of these types of methods. So one that I mentioned briefly at the beginning is I am working with this guy in petroleum engineering here at UT who is very interested in this problem of whether the volume of wastewater injection at a fracking well is causing earthquakes. Or they kind of know it's causing earthquakes, right? But how much is it causing earthquakes is sort of. And the problem, at least I think, fits a very similar structure to this. It's not really a public health, well, I guess it's a public health problem, but you know, we're not looking at health data or anything for this. It's just they know where the earthquakes happen and they know where the fracking wells are. But it does map to this type of problem. Another one is there are problems that come up like this in ecology, I think, where, as I understand it, and I've started to work with a couple of people who know a lot about ecology, where you have some ecosystem and you intervene in some parts of it, but you know that if you're studying some species in some forest, if you intervene at points in the forest, the impact on the species is not going to be confined to where you drop your intervention in the forest. It's kind of going to spill out according to how that species moves within the forest. So I've started to think about other problems where this type of thing comes up. And another one in water distribution systems, like water treatment, which is something I've sort of gotten involved in since moving to UT, where it's a similar thing. In principle, there's a lot known about the water dynamics of how water moves through like a municipal water system.
Mm-hmm.
You might drop some interventions in that water system and you want to know, sort of how it propagates. So those are areas I've started to think about where I think a lot of these similar problems, these methodological problems for power plants show up. What do I think of, what have I thought about it? I thought a little bit about COVID. I basically was involved. I'm nominally involved in like the UT COVID Research Consortium, funded by Tito's Vodka, oddly enough. But I've been involved in some COVID related projects, nothing that would like actually has that much to do with my sort of causal inference methodological interests. So I got involved in a little bit with some of the data on human mobility that was getting very popular right when COVID hit and all these companies started making their like commercial products of people's mobility via cell phones. They started making it available for research. So I don't know if you've been using data like that or exposed to data like that.
Not me personally, but we too are setting up a COVID research center. And others in the group have looked at those data. So
yeah, I dipped my toe into that a little bit. It's kind of a mess, as you can imagine. The only problem that I worked on in any real detail was, and we have this paper, we're trying to get out the door on it, but it's thinking about like when the first wave of COVID hit the US, so like back in March and April, a lot of things happened at once to try and prevent the spread. there were some like official stay-at-home orders, of course, like, you know, rules that were passed. And there was also people started changing their behavior as measured by some of these like GPS-based, you know, smartphone-based data sources. And we have one paper that looks at just that first wave, like from March through like, I think we go like maybe to the beginning of May, and tries to tease apart like, well, which was it that mattered most here? The fact that people stopped, like mobility changes as measured by these GPS things, or these official kind of policies that went into effect.
Or keeping schools open or closed. You know, that's a big issue.
So that was exactly what I had in mind, but rather thinking more about the reopening phase, and the various relaxations of those rules and what the effect was on the second wave.
Yeah, so I more or less have not thought about that type of reopening question all that much, except to know that one of the interesting and really thorny things about this. So with regard to the first wave, schools closing, bars closing, stay-at-home orders, whatever, they tended to all kind of happen at the same time in a given location. So there's not that much information for like, at least during the first wave, for trying to tease apart like, well, was it the school closures or was it the bars closing that made the biggest difference? So based on my experience, I'm not like, based on my experience using only like the early wave data in last spring, I don't think there's enough information to figure that out because it all kind of happened at the same time.
Well, now you will have the opportunity with the third wave of new lockdowns that are definitely coming.
Right.
To see whether there's any more information.
And so one of the things that's really thorny about this is, you know, you open up the Washington Post or whatever, the New York Times, and they had all these maps of who's social distancing where, right? And those are all based off this cell phone GPS data. Obviously, that cell phone GPS data is a proxy for people's behavior.
Mm-hmm.
But the thorny thing is the extent for which that's a proxy is also evolving over time. So like, you know, is somebody never leaving, if somebody was leaving the house, if you saw from their cell phone that somebody was leaving the house a lot in April, that probably means something very different than that person leaving the house a lot, you know, in October. Because if they're leaving the house in April, who knows what they were doing. If they're leaving a house a lot in October, they may be wearing an N95 mask, sanitizing their hands all the time, you know, only going places that aren't crowded. And that, of course, doesn't show up in the GPS data. And so you have this like proxy of human mobility that's supposed to measure social distancing. Clearly, it's imperfect. But the way in which it's imperfect is also clearly evolving over time.
So in your work on the first wave, what was the observational unit you used? Is this aggregate data?
Yeah, at the county level.
That's exactly what I had in mind doing for my sort of second wave analysis. So county by time.
County by time.
Probably week. Over what geographic spread? Because the other issue that concerns me is in order to tease apart the effects of different interventions, obviously we need some heterogeneity, and that would argue sort of for maybe a nationwide analysis. On the other hand, the data quality is going to be so highly variable across observational units that we have some difficult problems of confounding, it seems.
Yes, definitely. So what we did, again, focusing on the first wave, it was county level. We did 7-day rolling averages of deaths. We didn't do cases because there's an issue there, right?
Yep.
So we did 7-day rolling averages of deaths. We did county level data, aggregated data.
Over the whole country or just Texas or what?
No, so we did over the whole country, but there were some exclusion criteria. So we did over the whole country, and it was only counties that in the time period of study had reached at least a certain number of deaths per capita.
Mm-hmm.
Which again, during March and April and May, I forget, it's a few hundred counties.
And how did you deal with time delays?
We just specified something based off like what the epi literature said. You know, like a 10-day, I forgot what exactly it was, 10 or 12-day delay lag between when like an action happens and when we sort of look to see an impact in the death count. So, you know, we looked up sort of what's the average incubation time and time from infection to death on average, and we just pieced something reasonable together. We did not do anything fancy.
Has anybody looked at total deaths, not just deaths due to COVID, but, you know, the outcome? I mean, you know, there are people out there, and I'm not one of them, but there are people out there that say that, you know, the death, there's all these other comorbidities, and you're just, you know, renaming some deaths as COVID deaths when they would have been called influenza deaths, or some other, or, you know, some other issues.
I don't know whether people have looked at sort of finding evidence for whether that's true or not. I don't know.
I think there are studies looking at excess all-cause mortality, but I don't know if they've linked it with necessarily policy interventions as well.
Yeah. Yeah. I'd be surprised if there wasn't that stuff there. Yeah. But I don't really know it. I should also say before I forget that the main thing we were focused on in this one paper that I did was about the timing of the intervention. Because Duncan, you said something about you need heterogeneity.
Yeah.
So again, at least in the first wave, but I think still, you know, in the first wave, even though in calendar time, everything kind of happened at the same time, right? In epidemic time, there's tons of heterogeneity.
Mm-hmm.
So because the epidemic showed up some places way before other places, right? And so we defined everything in terms of epidemic time. So that was like time since, number of days since meeting some threshold of like, I don't know, some deaths per capita threshold. And the problem that we really wanted to try and figure out was the question of the time, not the effect of the intervention, like how many deaths did this intervention save? That was not the question we tried to answer, because I think the confounding, again, at least based off what we had and during the first wave, we were not going to resolve the confounding there. But the question that we tried to answer was, how much did the timing of the intervention matter? So like, what was different between the places that, you know, what would have been different in places that intervened at a certain time would have intervened 10 days earlier or 10 days later? I think we had a little bit more hope to say something, to like provide some evidence of that.
Well, the other thing which occurred to me is that sort of simple Poisson regression techniques were not going to cut it because of important time-dependent determinants of when the policies were introduced. It's just the same sort of issues, it seems to me, that Jamie and Miguel have talked about. And so something needs to be done to build, I was thinking in terms of propensity scores for the introduction of the different policies, in terms of past history, which could include past history of the epidemic itself, as well as just fixed covariates.
Yeah, I think you're right. Certainly for any future wave. So during the first wave, I think there's an argument that there isn't a ton to have been gained by that, because at that point, what was motivating the actions that were being taken was more like media stories than it was like actual case counts, for the most part.
Mm-hmm.
But certainly now, you know, what's been going on for the past week is obviously dictating the decisions that are being made today. And so it introduces all of this time-varying confounding, outcome-dependent, you know, time-varying confounding.
Are you aware of any other groups that are doing this kind of work?
From the sort of explicit, like, causal epi side?
Yes.
No, I don't know.
Well, I don't want to waste my time reinventing the wheel. And I don't read the literature, so.
I don't know of any. Yeah, I don't know of any. And I think that there is, yeah, so I don't know. And most people, of course, who are doing this with more epidemic models. They're not doing it with like statistical time series.
Yeah, that's what David Conti is doing.
You use SCIR models and stuff like that.
Exactly.
Yeah. That's what most of the people here at UT are doing. And so we wrote this thing that's like a pretty, not particularly complicated, but I think very rigorous, like, you know, hierarchical model with a, you know, sort of polynomial interrupted time series type thing. Again, quadratic polynomial actually does approximate the epidemic dynamics right at the beginning of the epidemic. It stops being a good approximation a few months in. So how do you model the shape of an epidemic curve statistically? I don't know. But that was another sort of convenient thing about doing this during the first wave. There was a lot of evidence that just a quadratic for the initial growth phase was actually pretty good.
Yeah.
Well, I was glad to hear you mention hierarchical modeling, because that's a component of David Conti's work, where there is a bit of estimation of the various epidemic parameters that are required. And the idea is to try to borrow strength across different jurisdictions, because there should be some similarity, although there will be great heterogeneity.
Well. And that's, you know, it's, I don't know, in my experience, it's tough to do this type of work because you write a statistical model and it gets reviewed by somebody who wants you to do an SCIR model, and you got to convince that person that your model is bringing something that those models are not that good at bringing. And I think the kind of hierarchical structure and borrowing information is one of those things. And at least we try to argue that in our paper.
Yeah, well, I think that's the point of Dave's work, that it's a combination of mechanistic, i.e. SCIR models, with statistical estimation involving hierarchical Bayes.
Good. Well, that's good to hear.
And all implemented with ABC estimation.
Oh, yeah? Even better. That's great. I mean, yeah, I mean, I think the student who programmed this thing we did it in Stan. And I was like, I thought that was pretty sophisticated for this type of literature, but ABC sounds pretty good.
Right. Well, they have a manuscript which I believe has now been finally submitted.
Oh, nice.
And if you're interested, I can probably share that with you.
Yeah, sure. No, it'd be great. I don't know how much I'm personally going to keep up with the COVID stuff myself, but
me too.
It's a fast moving world, that's for sure.
Yeah.
The COVID science.
Well, anybody else got questions that they want to bring up for Cory? Erica, you were late and missed a lot of it, but you can watch the YouTube recording as soon as we post it.
Well, I've seen, I think, a variant of this presentation earlier when you came and spoke for the seminar talk, a year ago or so.
Yeah, that's right. So you might be the only person who remembers, but yes, it was a variant on that talk.
I feel like I didn't really miss it.
Yeah, no, you didn't.
Except for maybe new stuff.
Well, thank you for doing this again. This was a fabulous talk. And I, for one, certainly learned a lot.
Great. No, thanks for asking me. This is fun.
Sorry, can I ask one more question? Do you have any effort based on the model you use to extend the interference work into time-dependent scenario? Have you started trying something like that?
We are trying.
Okay.
That's the next step. So one thing that everything that I sort of breezed through today assumes that the network is fixed. In reality, this network is not fixed in time. So two things can vary in time in this problem. One is the application of the treatments.
Right.
Power plants, once they install them, they don't take them off, but more power plants install them over time.
Right.
That changes. You introduce new treatments to the network, but the structure of the network itself changes like month to month because it's mostly based off the wind direction. So you have this, or at least seasonally, it measures. So which power plants you're breathing where you live changes in the winter and the summer.
Exactly. Right.
And we have the ability to characterize the time, like the sort of temporal variability in the network. And so there are lots of interesting questions because you could have these estimands that are around the introduction of new treatments to the network. And then you can also have estimands that are just around kind of changes in the upwind treatment, that G function, that are not attributable to the introduction of new treatments, but they're attributable to just the variability in the network structure. And so we're at very early stages of trying to figure out how to do that.
Okay. Yeah, looking forward to that.
Yeah, me too. I mean, I think it's pretty exciting to think about how to do that. I don't know. I mean, I don't know of any work in the causal inference network literature that takes that problem on. Do you know of anything? Have you worked on it? I mean,
no, there's no literature. There's one literature on that I can share with you, but yeah. It's not very rigorous, but it's claimed that they deal with the interference issue when they have a time-dependent treatment.
Yeah.
I think it's published in the system methodology in the medical research.
Okay.
I can forward to you that paper. We have a grant from CDC to study the antibody use effect on the inpatient visit. The outcome interest is the risk of antibody resistance. So it's apparently, so imagine that in the hospital setting, if your neighbor uses antibiotics, you are less likely to get infected and become antibody resistant, right? So that's why we have the so-called interference issue. So we have a study to try to address the direct and indirect effects of antibody use on the risk of infection and resistance. But we plan to extend it to the time-dependent structure, as since during the hospitalization, the patient receive the antibody at a different time point, not just one-time thing, right? They may receive the immediate intervention at the early stage, and during the stay, they may find another risk, and they will find another treatment to the patient. So this is a time-dependent treatment issue. Yeah, we have a CDC grant try to play around this, but we need to finish the first static one treatment issue, right?
That's great. Yeah, I mean, in my experience, because so much of this work is motivated by things that are like explicitly social networks.
Yeah, right.
And with the exception of like companies like Facebook, who can do what they want with data, as much data as they want, usually it's not easy to get data on social networks. So when researchers have it, it's usually a fixed point in time.
Right.
And I think it's relatively new that people, like the setting you're describing and like the work I'm doing, it's only relatively recent that people are getting this like network data that has the temporal dynamics available.
Right.
I think it's sort of wide open as far as I can tell.
Right. In the hospital data, from EHR data, we know where the patient stays. So we can kind of create a network in terms of the distance, like you live in this unit and how many patients live around you. So we can kind of create a network, but this really need a lot of data cleaning, data management effort. We haven't gone that far yet. So, right.
Interesting.
Yeah. Okay.
Cory, you mentioned on your references slide a second paper by Forrest here that you're a co-author of. I didn't see a citation. What's the status of that one?
I want to put it on archive and submit it this week or next week. I can send you a copy of it if you want. Okay.
Yeah, that would be nice.
That's the one that's more closely related to what I told, like the talk.
Yeah.
Basically the analysis of the talk. There's some other more general stuff about bipartite interference cited there that's been published in statistical science, and there's another one in biometrics that's more of a clustering thing, but the one that is this like reduced atmospheric model and the joint propensity score stuff, that one we've not submitted yet. Even though I've been giving talks on it for like 3 years. I don't know why I haven't been able to get it out the door, but it's almost done.
Well, thank you again. Any last thoughts from anybody? If not, thanks, and let's keep in touch.
Please, that'd be great. Thank you, everybody.
A
Thanks
lot
a
of
lot.
things in common here.
Gotta go for my next Zoom meeting.
All right.
Bye-bye.
Thanks,
Thank you.
everybody.
Bye-bye.